Welcome to Microlecture 45 on carbocation rearrangements. Okay, so this would be an example of a carbocation rearrangement. We see that initially the positive charge is on a secondary carbon, and we see that the neighboring or adjacent carbon atom has three methyl groups. Okay, one of them can shift over and take the place of that sort of empty p orbital of the carbocation. And so the electrons are coming from this bond and landing on the positively charged carbon atom. All right, and so we've moved that methyl group over to that carbon atom, and by taking the electrons from that bond away, we leave a positive charge on the carbon that it was attached to. Right, and so the trick is whenever we form a carbocation, we must look at adjacent carbons, and if you can move a group, it's going to be a hydrogen or a methyl. Usually, and there are some other carbocation rearrangements that occur, but they're usually small atoms or groups of atoms. So usually just a hydrogen or a methyl is going to move over, and that's going to allow a more substituted carbocation to form, which is more stable. So if it can form, it will form. And so it's just a matter of always looking to see on adjacent carbon atoms if you can do a shift that would allow a more substituted, therefore more stable carbocation to form. Okay, and on the other side, by the way, we had hydrogens. It would make no sense to move a hydrogen atom over, for that would place a positive charge on a primary carbon. And that would create a primary carbocation, which we know is incredibly unstable and never forms. So as long as you can go toward something that is more stable, toward a higher degree of substitution on the positively charged carbon, then it will happen. What you can't do is go farther down on the structure. So we can't look, to more than one carbon atom over. We wouldn't be able to look over here at groups that are way down here on the structure and try to think about moving any of these bonds. It has to be an adjacent carbon, one atom away from the positively charged carbon. So it can be kind of tricky to pinpoint these and find them, but let's do a couple of examples of this happening in reactions that you already are familiar with now. So let's say that we have this alcohol reacting with HBr, and so we've got HX and an alcohol, and we're thinking then SN1. Those are the ingredients for an SN1 type of reaction. Where we would pick up a proton first, create a good leaving group. We'll go through the mechanism. But what we would predict for the product in the past, prior to covering this topic of carbocation rearrangements, is maybe you would predict, I'm missing a methyl group here, maybe you would predict this as a product. Right? And it turns out that that does not form, and that the product is actually that. Okay? So let's figure out how it is that this product forms as our major organic product, and we get none of this other species that, at least at first, seems totally plausible. So the first step in the mechanism, of course, is to protonate our bad leaving group. We're going to activate our leaving group. So I'm going to pick up a proton from HBr, and I'm going to generate a good leaving group which places a positive charge on the oxygen atom. And the water leaving group takes off. These are intermediates, so I'm going to draw them in brackets, leaving behind a positive charge on a carbon atom. So we've got a carbocation here that is secondary. Whenever you form a carbocation from now on, you always look to adjacent carbon atoms and you see, if I could move something, could I generate a more stable carbocation? Well, if I moved one of the two hydrogen atoms over here, I would still have a secondary. I'd be going secondary to secondary. So there's no reason or driving force to do a carbocation rearrangement right there. But if I move this hydrogen atom over, I would be going secondary to tertiary. And so if you can, you must do that rearrangement, all right? And so the electrons from that carbon-hydrogen bond are going to come over here. The carbon-hydrogen bond moves, and the positive charge ends up on the carbon atom that we just removed electron density from. So it's going to be this one. Okay, and so the hydrogen atoms that were there are still there, but we have this more stable carbocation as a result. Okay, so 3 intermediates form here, and to get to the final product, the bromide ion comes back in for attack at the site of positive charge. All right, and so that's it. That's how we explain this other product. It's because of a carbocation rearrangement. And while we're here, it's worth noting too that this carbocation was also extremely stable due to resonance. So not only did we improve the stability of the carbocation by going from secondary to tertiary, but we also created a much more stable carbocation through resonance stabilization. So let's do one more example. This time we're going to use an alcohol and concentrated H2SO4, which you might recall are the ingredients for E1. Okay, when you see that reagent set, you want to think E1 reaction is going to proceed here. So we're going to form an alkene. And you might think, up until now, before we covered carbocation rearrangements, that the alkene that you would form is right here. The double bond is right there. It turns out that that does not form at all. And what actually forms is this alkene. All right? Again, the issue is going to be carbocation rearrangements. Let's think about the mechanism. So we are in H+. When you see H2SO4, think H+. So this oxygen is going to pick up a proton. We're going to turn that poor leaving group into a good leaving group. And then water leaves as the leaving group, leaving behind a positive charge on this carbon atom. And then we're going to go ahead and look at adjacent carbon atoms. I see if I moved my positive charge through carbocation rearrangement over to the carbon atom adjacent to the left, I would end up with a primary carbocation. So that's not an option. But if I moved one of these methyl groups over from the carbon atom on the right, then we could theoretically generate a more stable carbocation. Let's do that. You might be wondering too, well, we moved a hydrogen before, why are we moving a methyl now? Usually it's the smallest possible group that moves in a carbocation rearrangement. Okay, and here it's a methyl, but on the previous example, if I slide back to it, the smallest group that was available there was a hydrogen, right? We wouldn't move the methyl if we can move a hydrogen, so move the smallest group. All right, and here we have only methyls, so methyl was the only option. And so we're going to move the methyl over there. That's going to leave behind a positive charge here, and this is what our structure is going to look like. And then it's just a matter of finding a beta proton. So I'm going to draw that beta proton in there, and the conjugate base in solution is going to pick up that proton and kick the electrons inward to form the double bond, satisfying the lack of electrons on our carbocation. All right, so hopefully that helps you understand carbocation rearrangements and helps you identify them, but always look for them whenever you generate a carbocation in any reaction, even if it's not SN1 or E1 in future reactions that we cover. As soon as they form, they can rearrange, and if they can rearrange to form a more stable species, like in this case, we ended up with a tertiary carbocation here. If it can, it will.